Okay, I think we can start slowly. It's with great pleasure to have Pedram, host Pedram today, Pedram Roushan from the Google group. We'll go back some time. It's really nice to have him speaking to us about different things. I think he mentioned a few things about the result last year on the quantum supremacy and what's under the hood, as he called it. And if time, he will speak a few about other things as well that these guys have been looking recently. A brief introduction to Pedram. Pedram, I need your help here. I forgot. You came to the US roughly 15 years ago.
Yeah,
right?
15, 20 years ago, yeah.
Right, a long time. Then you did your, you studied in Pennsylvania. Was it Pennsylvania, helping with
yeah, University of Pittsburgh.
Pittsburgh, right? You did your PhD there. And then you were in Santa Barbara. And now you are in Google since the last, 2015 or so.
Yeah,
right.
Yeah, 6 years ago.
6 years
2014.
ago. 2014.
Yeah.
So without further ado, we can start. And please.
Yeah, I'm happy to answer questions during the talk. Dimitris, thanks for inviting me. Of course, I wish I was in Singapore, but you know.
It would be nice to have you back again like last time. Not Sycamore or Greek dinner this time, but hopefully
this mode of this way of talking also has its own advantages. As Dimitris said, I'm a member of the Google quantum team. The team is this is some of our picture of us taken in Los Angeles is a team of hardware engineers, physicists, material scientists, and theoretical physicists who are working toward the common goal to advance quantum technologies toward making the first quantum computer. Also, we are very actively looking into NISQ applications and try to figure out, even without error correction, what can be done. And we are very actively searching in this area, and I encourage you to share your ideas or your works on that with me too. But as you know, there was a work published by us in the in Nature. In fact, tomorrow or Saturday, well, you guys live in tomorrow always. Saturday is the first anniversary of the work, and we are very happy about it. The title of the work is Quantum Supremacy Using Programmable Superconducting Processors. I understand the phrase supremacy has been a bit sensitive, and I try to avoid using it, but please take it easy on me. We have been saying it for many years, and just try to replace it. It could take me a while to get used to it. Anyways, what is important is that the data that was analyzed during this work is also available, and the paper is also open access. So I encourage you, if you have time, to look at the data yourself and try to analyze it, although you might need a supercomputer for that. Let me start with some preliminaries on how to go beyond classical computations. And the question that we are trying to ask in going beyond classical is rather strange when you think about it. We are trying to say we are incapable of doing something. So that's really strange when you think about it. How can you say that you failed to do something, and how do you know how you're going to distinguish that from not working hard enough, essentially? So I try to make it clear that the experiment, now we call it going beyond classical, it has actually really solid foundations that I will explain to you how it came about. First of all, I want to say is about a well-defined computational task. It's not it has really well-defined goal to it. It has it is precisely defined. Also, it's done on a programmable processor, meaning that very similar problems, a group of problems and the algorithm can be done on this processor. And then to the best of our knowledge, the cost of doing the experiment is really prohibitively large on a classical computer. Maybe it can be understood better if I bring some examples. Compute water and ice for me or something like that, as vague as that, really doesn't qualify it as a beyond classical experiment. It has to be really well defined. What about water? What about ice that you want to compute in this case? Let's say you also teach your dog to give you a high five. That's great. Congratulations to you. But it really is not a programmable task that we are really talking about a group of algorithms, class of problems that can be mapped to this processor. Also, we are all physicists and we all love critical phenomena, phase transition and whatnot. And sometimes we do experiments close to phase transition and we say, hey, look how interesting it is. As interesting and fascinating it is, it might not be a computationally hard problem. In particular, this example of quantum phase transition that some of our colleagues looked closely at as a way to simulate and show the power of their simulators. Close to criticality at all the scales, the system behaves the same. So in fact, you could even write mean field theories or so usually, and it's not a really hard problem. So you have to be really careful in choosing the problem to be assured that it's computationally hard. For instance, a good example is the Boson sampling that came to existence as a result of works of Aronson and Arkhipov in 2013. They figured out that if you inject photons into an interferometer and ask at what detectors these photons are going to come out, is going to be a computationally hard problem because they found a way to map it to a permanent of a matrix, and is known that finding a permanent of a matrix is an NP hard problem. But it's very subtle. If you say, okay, I got it, you shoot particles into interferometer and then ask where it come from. If you replace the photons, bosons, with electrons, fermions, and say, okay, I shoot electrons into an interferometer and ask where they come, that problem becomes easy. That's changing something so subtle. So you might think that the problem must be hard, but the fact is it's not. So finding hard problems happens by elimination. You just have to be sure. There might be a day that someone wakes up and finds and saying that was not a hard problem. So you can essentially never be sure. So this is rather very subtle, and at the end of the day, you have to just believe that something was actually computationally hard. But the experiment we did, or any beyond classical experiment, has two pillars. One is the pillar of complexity, and another is the notion of fidelity and doing it with high precision. You see, you can look at the waters coming out of a fountain, and that is extremely hard to predict. Where are the waters? How do they break? How do they come back? What is the velocity of each patch and whatnot? Sure, so you have generated a very complex problem. It doesn't necessarily, it's very easy to generate something like that in the lab. It's essentially you're just making a mess. It's not that hard. You can throw your keychain in the air and ask how it's going to land. That's a very hard problem. But the beyond classical experiment is about fidelity and controlling it. You have to show that you can do this in a controllable and with high fidelity. And I explain how we are checking in that before I show you the experiment. But one thing we do to assure complexity, one at least a necessary check, is that there's not enough. We remove symmetries in the problem. We take away the symmetries in the problem. You might know that if you have a very symmetric circular billiard table and you shoot a ball in it, the ball is going to, even no matter how long you wait, is going to avoid going to the center of this circular billiard table. However, if you have a stadium-like billiard table, if you wait enough, the ball is going to go all over the available space for it. So in one case, it can be simplified, means there are hidden symmetries in the problem that you may not be obvious to you, but they exist there, which allows you to simplify the problem. So so the problem can be done on a smaller Hilbert space in smaller computationally available space and can be simplified. So one thing that we're going to check to begin with is to be sure at least all available dimension of the Hilbert space, in our case is 10 million billion dimensional Hilbert space, is actually getting used. How are we going to do that? I'll get to it soon, but let me tell you the well-defined computational task that we considered for this case, for our beyond classical experiment. We have a grid of qubits. 54 was intended. One of them didn't make it, so 53 qubits. And we apply a sequence of gates, sequence of operations, single qubit rotation, 2 qubit rotations, you see with boxes and dumbbells or connecting rods. And we start the qubits in the state of 0000, a bit string of 53 length. And after these operations, we're going to measure all the qubits, and we're going to is my mouse visible to you?
Yeah, yeah.
Okay. We're going to ask at the end of the day, at the end of the experiment, which takes about maybe a few hundred nanoseconds, what is the state of the qubit? You're going to get a bit string, which is again 53 length of 0 and 1, and you're going to repeat that experiment maybe 10 million times for a given set of circuits. These rotations are randomly chosen. The 2 qubit gates are close to ISO-op. They're not exactly ISO-op, they're close to ISO-op. And there is a work by I think Vazirani. What I write in yellow means don't ask me questions. I don't know anything more than what I have written. So you just read it, you know, as much as I know about it. I think there's a work by Vazirani's team showing that this problem is sharp P hard, meaning hard. I don't know what it actually really means. So this problem can be not simplified. So that's the problem we're going to do. We are going to claim that we can predict the output bit strings better than a classical computer. But going back to the notion of uniformly exploring Hilbert space, the ergodic situation, can we be sure that the Hilbert space that is actually there is actively used? So here's an experiment done on a smaller subsets of qubits. You can take 6 qubits, you can take 9 qubits or 12 qubits, and you can choose a circuit, a sequence of gates, run on it, and measure the outputs over and over again for that circuit. And then you see some bit strings appear more than others, and you just count them, and here's just a histogram, not normalized, of the bit strings that comes out. So if the dimension of the Hilbert space is small, you can make probabilities out of them, not that problem. So you go to 12 qubits, the dimension of Hilbert space is about 4,000, and you, but still you can see which bit strings are more probable than the others. The information or the verification that the Hilbert space is uniformly explored is embedded in this plot, is already in here. So let me show you. So we're going to sort these things, right? I have a counting scheme. I started from 0, 0 all the way to 1, 1, 1. You could have had a different counting scheme. And the pattern you see here doesn't have any deep meaning to it. But you know, I can just sort them out. I can put more probable bit strings to the left and least probable ones to the right. This is after one circuit, you get this thing. Now there is a theorem, I'm not going to go into it, which says that if you're uniformly exploring the Hilbert space, the shape of this data that you can see as a limit of large bit strings is reaching to a you can assume a curve going through it. It has a certain shape. In this case, it would be a logarithmic case. It would be a logarithmic, and that is essentially a signature of uniformly exploring Hilbert space. Here is a line of reasoning. After you applied your circuit, the output, no matter whatever the dynamic is, the unitary dynamic would give you a wave function, which can be written as a prefactor is a complex number Ci times all possible bit strings. That's an orthonormal basis. That's how it can be written. There is a theorem which says if and only if you're uniformly exploring Hilbert space, these coefficients forming a Gaussian, this real and imaginary part of these coefficients forming a Gaussian, and if they're forming a Gaussian, then you can the amplitude of them, the real part, the magnitude of them, sorry, would form an exponential. And well, this is the histogram of the probabilities. I'm not going to make it more complicated here. It means that this curve that you see here going through these lines would be logarithmic. So I'm going to measure the distance between this distribution and a logarithmic distribution next. Here, this is called Kullback-Leibler divergence. Is a way of measuring how two curves, how two probability distributions are close to each other. So Qi, let's say, is coming from logarithmic, that I say, from the Porter-Thomas distribution, and P is coming from what we have measured. So for the 2-qubit entangling gate, I chose two different ones. One, it was a square root of I swap. Another was I swap, which is close to what we have done in the beyond classical experiment. So you see, as a function of cycles, the number of times we are applying these gates, and as a function of size of the subsystem I'm considering, the distance between probability distribution that we measured versus distance from a logarithmic distribution drops to a very small number and then very gradually comes back. The comeback is down to the coherence effect in the system, where it takes you away from unitary dynamics, and you have to consider open dynamics and whatnot. But you see, when you're using the ISWAP gates very sharply in a very few steps, you're really reaching very close to Porter-Thomas distribution. You're really going down. And when you do the slower gate, square root of ISWAP, it takes you twice about the same time. So the gate used in the beyond classical experiment is extremely fast in getting to the dimension of the, in getting and uniformly exploring the Hilbert space.
Pedram, just a quick question. Give you some time to breathe as well. So
sure, yeah.
NQ is the number of qubits. Is this 1D, 2D? Is it the full Sycamore?
No, that's a good question. No, NQ is a subset of qubits, randomly chosen, subset of connected. So 10 could be one-dimensional. You go to the Sycamore chip and you just name 10 qubits.
So you pick guys from the Sycamore chip and you...
Yeah. It could be 1D, it could be 2D, whatever. But they're connected. They're not two islands. They're one patch.
Right, and then you hit them with how many? All of them are being swapped or square root swapped, or like?
Yes, that's a good question. You apply this pattern of gates.
Okay.
Well, maybe future become more obvious.
Right.
As you apply, well, when one qubit get entangled with others, yeah, there's not much you can do. One qubit cannot have entangling gate with two other qubits at the same time. So you got to kind of wait for the next cycle to get it involved. I'll show you in a second in a full pattern. Yeah. So
but you pick some sort of paths within the Sycamore chip that you say, okay, I'm going to pick this 5 in this wiggling now, and this 7, and this 10 or 9. Some of them could be straight lines, some of them not. You pick them, I guess. Is there a way that you pick them? You think that the best, or you control them best?
No. This is really insensitive to the choices. Yeah. If you really pay close attention, maybe there is something in one-dimensional versus two-dimensional, but I didn't bother with that.
Okay.
I think I get back to the pattern of how we're applying gates quickly. Let's see, what is this about? So, okay, so this is about tests that we have done, and I can show you more on uniformly exploring the Hilbert space. So this is about ergodicity, about being sure that the Hilbert space is not wasted, is actually actively used, essentially. The other notion I said was fidelity. So we get a bit string, we have to compare it with something coming from classical computer. We have to be sure that this is the bit string that meant to come out from that circuit. And as you can imagine, as the circuit gets larger and larger, this becomes harder and harder. But how do we do that? Well, you have probability of measured bit string. A bit string showed that frequently, so you can associate a probability to it, and you compare it with the probability expected from a classical computation. And you do this, I think, is for Neumann entropy. You compare them, and it tells you that how good what you got is compared to what it should have been. And the actual formula has a little more into it. You have to normalize, and you have to consider the fully decoherent case, but the essence of it is coming from comparing the bit strings that you measured versus the bit string that you should have got or was more probable or less probable. But if you have read the paper, the equation 1 is slightly different than what I'm showing in here. And the reason is that we are at the limit of 10 million billion dimensional Hilbert space. So you get a bit string and you don't know if that bit string, you're not going to see probabilities. You're going to do 10 million measurements or 1 million measurements. Not bit string, no bit string is going to repeat itself twice. So the formula in that limit, assuming Porter-Thomas distribution, assuming that your full ergodic dynamics, the formula takes a different form. The measured bit string, or a bit string that occurred, you measure, you know its probability from a classical computer, and this is how this fidelity gets obtained in this relation. Okay, this is getting, this requires knowing the probability of bit strings. So it's really hard to do when the system gets large. How do we do that? Well, it happened that there was some lucky event or some lucky, there was something that we took advantage of. And this is the patterns that Dimitris asked me 2 minutes ago on how these gates are applied. You see, you can apply A, B, C, D. I don't see under this is a C, D. You can the color shows that which qubits get entangled first, and then you do B and then C and then D, and then you repeat again. But it's really sensitive how you repeat the pattern. Okay. And one of them, it happened to be classically simple. Another was computationally extremely hard. So it, as I was mentioning before, is extremely sensitive to these choices. Okay, so let's see what we got. The first thing we do is to try to fit it inside a memory of a computer. So we do not apply any entangling gates between the left side and the right side of the chip. So you have two sets of qubits which are essentially disconnected from each other. This is called the patch circuit. This is that configuration. And you can, in that case, is essentially you're dealing with 20 some qubits. Is not hard to compute. I think 1 million or 10 million times we did the sampling, and then you can compute the fidelity. There's no problem. The problem is really breaking down into two patches, rather simple. So you can make change the system size, or you can change the depth of the circuit, and you can compute the fidelity. That's beautiful, not that hard. In the elided circuit configuration, we do not apply the entangling gate in the first few sequences, in the first few cycles. And you know, the left side and the right side evolve independently for, let's say, 5 cycles or so. And then from that moment on, you apply the entangling gate. And that is enough simplification to be essentially allowing the computation to happen rather easily. So again, you can see in these cases also we can compute fidelity. In the full circuit, Did I click twice? In the full circuit, we do apply all the gates at all time. And only if the pattern is EFGH, EFGH is what we can do. We can compute the time, we can compute fidelities. But when the pattern is ABCD, CDAB, we would not be able to compute the fidelity because it's just too hard. It's just would take a very long time. But however, unless there's not any reason to believe the fidelity of these two cases are different. You know, you just change the order of the gates. You don't think that you would really mess up the computation, mess up the setting of the problem that bad. They're not that different. They're just a little different in the order they are applied. So in terms of error produced, in terms of fidelity, we believe, and we only believe, that the red points, if they meant to appear, if we could appear on the right side, it would have been appeared in here. However, to verify that, it takes a prohibitively long time. You might say, wait a minute, your bit strings are not correct. Your bit strings are, 1 out of 1,000, kind of roughly speaking, are correct. And you're asking classical computer to do a precise computation of the wave function. That's unfair. You can allow the classical computer also to produce error. You can allow to produce a bit strings output with the same fidelity. It's a simpler problem. In fact, it just got simpler with a linear factor, with like a productive factor of fidelity. Problem get 1,000 times or so, or 100 times or 1,000 times simpler. Again, when you go to deep enough, to 20 cycles, these 10,000 years, which we mentioned in the abstract of the work, is really, again, pops up and shows up and become hard again. Okay, so that is our claim to being beyond the classical limit. What is very interesting, and that is for quantum computation and what we call it the verification of the digital error model, is that we could have predicted that fidelity by multiplying the fidelity of the individual components. So the error in the entire system is not worse than the error of the individual components. If you just multiply error single qubit readout and 2 qubit gates, I don't know, G1, you do this multiplication, you would arrive at this black line, which is very quickly we could arrive at because it's a local computation of local errors, and it's exactly predicting the fidelity of the chip, fidelity of the entire operation when you're applying all the gates simultaneously. So, or running the full algorithm. That's really encouraging news, meaning that there is no hidden, mysterious, more sources of noise and error in our chip. Okay, just to be more concrete on the computational side and give you a sense of how long it takes to do these computations, let me walk you through the time it takes to do such a computation with a classical computer. If one way of doing the computation is just to solve Schrödinger equation, the full wave function, and just see what happens. This is not very sensitive, this computation, on the number of cycles you apply, how deep you go, but it quickly ran out of memory, meaning that if I had 53 qubits or so, the computation would take about a day to be carried in a computer. However, that computer has to have a, the computer which has 1 million core. The colors are based on a 1 million core computation. It would take about a day, so it's not that bad. But then it needs memories which is beyond the RAM available in any supercomputer on this planet. So you might need to do your computation in a different planet. Even laptops are not doing that bad. You know, if you have 2 cores in your laptop, up to 30 qubits or 35 qubits or so, the computation seems to be taking about an hour. So you just do a brute force, you put the wave function in your classical computer, your laptop, it can do the computation. But the problem is your laptop doesn't have that much RAM, and it just quickly ran out of RAM. And you can see, you know, in 1980s, this could have been done to the level of 2 unique qubits. It's just a matter of fitting in your memory, in your RAM. I have to emphasize, the computation has to be in the RAM of the computer. Otherwise, you cannot send back and forth between RAM and hard. That would take forever. Okay, that was not very smart. A smarter way of doing the computation is to some method called I don't see the top of the thing. Yeah, how do I do that? Okay, Feynman something that is inspired from the
Feynman, yeah.
Schrödinger Feynman is inspired by the Feynman path integral or associated with that, which is says, look, you break the space into 2. You have left qubits, right qubits, and you consider all the ways that left could have interference with right. And you consider all the paths that connects these two, essentially. Okay, the space, the volume it takes to store the wave function become much better. You're dealing with the smaller sets of qubits. And you can see on the top axis, we are doing much better on memory. But on the time that it takes, you see when you're going deep and deeper, now it becomes shows some time dependence, and the red regions are migrating and making the whole plot red. So sure, you can play things, you can fit the memories, that's better, but then you lose in time. And the computation we actually did to verify this wave function is halfway between these two. Here is going back to the error discussion, that, you know, these things has to be more simplified. So on the left, I have what I had before, and I'm just telling you that let me allow error to happen and allow simplification down to occurrence of error in classical computations. And you can see that things are getting simpler and simpler if you allow more error. So we are somewhere in between these two 2-qubit gates. We had was maybe about 0.9% or something, yeah, 0.9, about 1% error. If you have 2% or you have 3% error in the gates, in the entangling gate or in the entangling gate, you would see that the computation would not be hard at all. Classical computer can beat you, no matter at up to 70 qubits or up to depth 30. So it's extremely sensitive on the gate error you make. And we have taken this into consideration. Okay. Another thing comes back to the, you might think to the notion of sensitivity to gates. You might say that, well, look, maybe no matter what you do, you're going to get these bit strings, and it's not really that sensitive to errors in your system. It's really, there is a basin of attractions, and you're always going to end up there, and you could do all these precisions, but kind of, you may not need all that. Here is an experiment that we changed one gate. We took a single qubit gate, and we changed it from square root of x to, let's say, square root of y, or square root of w, which is somewhere halfway between. And we look at the fidelity, and we see that the fidelity drops by 2 orders of magnitude. So this is the notion of quantum chaos, although I don't like the phrase, but is really hypersensitive to the Hamiltonian and perturbation in the Hamiltonian. You make a small change in the Hamiltonian of the system or the unitary of the system, and you can see that the fidelity drops by 2 orders of magnitude. In fact, this has been predicted by Antonio Salieri. He said that you make a small displacement, you make a small changes, and you see that the whole thing falls apart. Some people said he said that about Mozart's compositions, but now we don't know if he had this experiment in mind, or Mozart's composition. So we can discuss that. But anyways, that's something to keep in mind. So let me summarize the experiment. And this is it helps you to figure out where we are. And when you're proposing your NISC algorithms, you can see that how far we are from whatever experiments happen next cannot be orders of magnitude different than this. We used 53 qubits. We applied gates for 20 cycles, which came to about 1,100 single qubit gates and 400 entangling gates. And we predicted fidelity based on multiplication of the simple qubit fidelities, and whatever we could extrapolate from XCB and other methods is also consistent with it. And we essentially say that we are challenging the extended Church-Turing thesis. The extended Church-Turing thesis says that it talks about efficiency of doing the a computation on a classical computer. Okay, so I'm done with this part of the talk. Let me see how I'm doing in time. Okay, 20 minutes.
You still have 20 minutes, yeah.
Right, let's see. Okay, okay, let me try hard going faster maybe. So let's understand what's happening during this experiment in the language of chaos and propagation of entanglement, or scrambling of information. So if you want to quantify how scrambling propagates in this case, the departure point would be to start going back to look at classical chaos. Edward Lorenz, one of the pioneers of chaos, to formulate, to communicate his ideas, he used this analogy in one of his papers, saying that if a butterfly flaps its wings in Brazil, are we going to get a tornado in Texas or not? So essentially, he's trying to say that there are systems that are hypersensitive to initial conditions, initial states. So we can try to capture that with quantum mechanics. We create initial state psi naught, we evolve it with the Hamiltonian, we arrive at psi 1. We create a slightly different initial state, psi naught plus delta psi naught. We evolve it at the same Hamiltonian. We arrive at psi 2. This is like the initial condition corresponding that a butterfly flap its wing. And you look at the overlap of these two at the end of the day, psi 1 and psi 2, and it happens to be you get the same thing because U and U dagger in between, they cancel each other out. So this notion of chaos, hypersensitivity to initial states, cannot be extended to quantum systems. So we have to think about something else. The simplest case that you can do, I think, for quantum systems is to think about the Heisenberg picture. And in the Heisenberg picture, where operators are evolving and the wave functions are stationary. So if they're butterfly flap its wings, and you have two operators, V and W, so W is for wing and V is for vorticity, I guess, according to Monica. They commute initially in the Heisenberg picture, and the operator W grows, perturbation grows in the system, and later on when you measure it, W and V don't commute anymore. Okay. But you know, in the lab, I need something in the Schrödinger picture. If you translate this problem that this setting that I explained in the Heisenberg picture to Schrödinger picture, means that you have a wave function that you apply V, and then U and U dagger sandwiches W, and then you get psi 1, and or you change the order of V and W, and you get psi 2, and you have to compute the overlap of these two. So this, the left and right are equivalent of each other, Schrödinger picture and Heisenberg, and they are related with a simple identity that I have written in here. So that's what we are going to measure to capture how scrambling happens in the system or how perturbation propagates in the system. So as you see, there are two gates, there are two operations, sequence of operations. One has V before W, one has W before V. And they cannot be done simultaneously unless you introduce an ancilla qubits. This ancilla qubit acts as a quantum clock, which you conditionally couple to it, and this CZ conditional Z coupling to it allows forward evolution and backward evolution to be recorded at the same time. That's a proposal. I'm sorry, I'm missing references in here. That essentially captures the Bose physics. So essentially, the experiment we are doing with this pulse sequence here is that it would be equivalent of dropping an oil in a glass of water, and it diffuses, and then you're going to reverse the arrow of time. If there's no butterfly in between, there is no flap of a wing, is a quantum unitary dynamic. It's just going to come back and it's going to fully come back. However, if there is a butterfly in between, it's not going to come back to where it started, and that is measuring, that is used to measure ergodicity, propagation of entanglement or propagation of disturbance, perturbation in the system. That's the experiment we are about to do. Let me show you the simplest case possible. For the entangling gate, in this case, we choose a CZ, which happened to be its inverse. So for M layers, we apply these. And then after a butterfly operation, we start to invert it, and we always measure at the ancilla qubit connected to the first qubit. So here is this pulse. Here is the result we get. So there's an ancilla qubit, which the measurement always happens at. And then we want to know how long it takes for the perturbation from the butterfly qubit, which is going to move from qubit 2 all the way to 20, it's going to make it to qubit 1. As you can see, when butterfly is close to qubit 1, very quickly this signal out of time order correlator, which is essentially measuring sigma y on the ancilla, gets to qubit 1, and this signal drops to 0. This is the commutator I talked. First, they don't commute with each other, and then at some point, boom, all of a sudden, they commute. So you can see as butterfly go further and further out, it takes longer and longer for the perturbation to reach to the left end of the chain, but eventually it gets there and the perturbation arrives at that site. And you can, is the commutator of V and W or W and V. You can also think backward on how long it takes from qubit 1 to get to the other qubit. So to be full justice to the proposal, thing didn't look beautiful in the beginning. There was a normalization curve that we have to compute, that we have to, measure and divide things by the normalization curve. Normalization, this black curve, allows us to do error mitigation, which is the case where there is no butterfly. So theoretically, it has to be totally flat at 1. But it captures the effect of decoherence and readout error in our system. So there is a division we do to arrive at the plot on the right. This is a powerful technique because it allows us to distinguish different choice of gates. So you can use single qubit gates that are coming from Clifford set, or they're coming from ergodic sets that in 1D what they're going to do, and they leave very distinct marks. They have very distinct OTOC signatures that we can measure to see what's happening in our system. And we are using this technique these days to characterize how entanglement propagates, how OTOC propagates in the chip. So that's a study that is going on. Let me see. Okay, 47. I think I have time to very briefly, maybe in 5-8 minutes, talk about the work that our former grad students and current Google employee Ben Chiaro did in collaboration with our colleagues, mainly from Europe. And this is a study of many-body localization. It's interesting to give you a flavor of what experiments we can do in the realm of condensed matter or chemistry or non-equilibrium dynamics in this case. So to inspire you to think about similar applications of our chip. This question comes to a study of many-body locality. The question is about understanding how ergodicity breaks down in a system when you introduce disorder. The fundamental assumption of statistical mechanics is that all microstates are equal probable. But it asks for this assumption and then builds everything on top of it. It doesn't tell you which systems have that and which systems don't have that. And for many years, we assume when the systems are ergodic, obey the ergodic hypothesis, they would be obeying the fundamental assumption, meaning the systems that are uniformly exploring their available microstates. And we know one case that it was breaking since 1958, the work of Phil Anderson. We know that the system, when there's no interaction between particles and you introduce a small amount of disorder in 1D or 2D, the system goes localized and ergodicity breaks down and the system stays away from equilibrium. And the whole fundamental assumption is not applicable anymore. For many years, we were told that we don't need to be worried about that when it comes to interacting systems. Interacting systems always thermalize, regardless of existence or not, absence of it, regardless of dimensions. And well, in 2006, they told us to be worried about it. They may not thermalize. You know, I'm butchering history, super simplifying it, but I think I'm experimentalist, I'm allowed to do that, it's okay. But essentially that led to lots of the studies to understand dynamics and checking essentially ergodicity in interacting system in the presence of disorder. Okay, I need to be a little quick in here. Let me see.
It's okay. I mean, we can take 5 minutes more if need be.
Okay. So here is a chain of 9 qubits, and the dynamic. So I'm putting the notion of gates aside, and we're just going to use the dynamics in the system, which is close to the native dynamics of the system, which is the Bose-Hubbard dynamics. And you can see that. As you introduce disorder, W is the strength of disorder, G is the coupling strength. The system fails to reach the equilibrium value, and some local observables that we measure is not reaching to its equilibrium value. Here's the asymptotic values as a function of disorder. You can see the asymptotic value of this local observable gets away from its thermal value and is stuck somewhere else. As disorder gets stronger and stronger in the system.
So Pedram, this sounds very close to what we did together a couple of years ago. Is it as new results or is it the same data or what's the new?
No, these are new. These are
same
new
Hamiltonian,
results.
Right? Is the
same Hamiltonian. Same
physics. Disorder, same. Okay.
But I'm trying to rush to get to the last slide, so you to hopefully pleasantly surprise you with some cool physics. So I don't want to disappoint you.
All right.
So in this physics, right, going beyond the work that we did with Dimitris and Victor and Girowatt, to go beyond that physics. So when you introduce disorder, you localize. However, there is a dynamic, there is a very subtle dynamics going on. And in that sense, the interacting systems are different than Anderson localized case. And we're trying to capture that physics in here. The wave function of these localized sites in a natural language to speak is called the tau effective Hamiltonian, is written in some tau bases. And these tau bases, which is almost like a Z basis, but there have these long tails which extend beyond a single qubit site and allows to have some dynamics, some interaction between qubits that are still far apart from each other in contrast to Anderson localization case. So I'm trying to pull that physics out. So the experiment to do is you put one qubit on equator and you do some dynamics and you measure its reduced density matrix. And you do it under two conditions. One is that there is a remote qubit at site J, a few sites away from it. You flip that case from 0 to 1. In the Anderson case, it wouldn't care less if something remote happened somewhere else. It's a non-interacting physics. Here, it should care. And you can see that the local observable that we chose on the site I is showing a different behavior. And we're going to measure this difference, and we're going to attribute that to this Jij tilt and kind of measuring this overlap, this gray region directly. That's the title of the paper. Okay, so here is this Jij measured as a function of the essentially free spinning precision frequency of the qubits I in two cases subtracted from each other when qubit J was in state 0 or versus when it was in state 1. And you can see, sorry, the axis is I minus J, the horizontal axis is I minus J, distance between two sides. And as I go further and further, we are able to measure this Jij overlap by the technique I just described to you in a chain of 15 qubits. We can put Ben's data on logarithmic scale, hopefully to impress you, to see how well we can go, and very small sub-megahertz things we can measure of the difference of these things. I think here's the same plot, but different data with the two different values of disorder, and we are putting in linear and log scale, so you can see that we can really measure 6 sites apart, small fraction of megahertz. They are different from each other, yet we can measure. And we can form a histogram of them. What Jij values would you get? Oh, what happened here? There's something missing in here. I don't know. Something got funny. As a function of separation between the two qubits. Sorry, this is a histogram. There's something missing. Let me move on. But also, as I claimed, there is some dynamics between these sites. So here we're trying to pull out the dynamics by measuring entanglement of formation. Entanglement of formation is something that we are very proud of to measure because it's an affirmative signal, meaning that these qubits, of course, are evolving in an open system dynamics. At the end of the day, they're getting coupled to their environment that we don't want to, but they're getting coupled to. But this affirmative signal, which is entanglement of formation, allows you to pull out how these two qubits only couple to each other, only entangle with each other, and would not be recording false signals that are coming from other sources of entanglement. So you can see, for instance, you start with a chain of, I don't know, 10 qubits or so, yeah? And you ask how long it takes, what's the entanglement between A and B1, B2, B3? And you can see as time goes in this logarithmic axis, initially they are not entangled, and they start building some entanglement, and then the entanglement goes down for two reasons. One is that, well, for one reason, I guess, because entanglement, there is something called monogamy of entanglement, meaning that you can't, when you start entangling with other qubits and environment, you lose that resource, so your entanglement goes down. So this as a result of decoherence and getting entangled with other qubits, this comes down. And here you can see a case that we are slightly going 2D. You can see entanglement, qubit A now has chance to entangle with more other qubits faster and more effectively. So you can see it doesn't get chance to build up that much. And also, yeah, it's also slightly happening at sooner times. Here you can see we are going quasi 2D or 2D. That A gets entanglement, and we can really tiny resolve these things. And you see now between qubit A and B3, in the midst of 15 qubits, and as it gets entangled with the whole things in the fridge that we don't like, still you can resolve that tiny signal if you average correctly, and that's very encouraging. Okay, some of you might have written a paper saying that MBL can be used as memory because there's some memory effect into these states. Sure, so we try to measure it to see how good it is. We create a Bell state and we measured what happened to this Bell state as time goes by. Let me see, what did we do? So this is a Bell state created, and we measured logarithmic negativity or coherent information is measure of how entanglement is preserved in the between qubit A and B, which we, I think, originally, yes, we put them in some Bell states. And then we look at them, how long it takes for them to decay. So there is some decay rate. This decay rate depends on the other dynamics in the system. If you have other photons in the system as we are changing their position. So we put a photon in these sites and we get them closer and closer and closer to mimic some sort of realistic dynamics. You see the decay rate goes faster, down faster and faster. Okay, so you might wonder, what are these things I'm plotting on the vertical axis? And I think I can show you the formula. It's not very informative. You can ask Michael and he would say, I don't know, it's something that theorists do. It's a job security thing that they're so complicated. I ask repeatedly, can we measure something more straight? These formulas of these are not intuitive to me. So just they're measuring how entanglement is preserved in the system. And you can see that, you know, it's preserved to a good degree for 300 nanoseconds, but they're not preserved infinitely. Okay. I can get back to that if we have time on thing. Well, but let me stop in here, conclude that, and then I'm happy to take questions. So the quantum supremacy or beyond classical experiment was finished a year ago, and we are very happy about that. But I want to say that this is really achievement of the community, not only those who work on superconducting qubits, but all of the quantum information family, which is, I don't know, a few thousand people working close with us, or we benefit from their comments and suggestions and discussions on hallways and whatnot during the past 20 years or so. And we really believe going forward and advancing quantum technologies, again, needs the effort and collaboration between the entire family of however many thousands they are. And to show our commitment that this is really not just words that I'm saying at the end of a talk, we do have various ways of engaging and working with the community. And here I wrote some of it. Feel free to reach to me, and I put you in contact with relevant people that would tell you about these ways. So, you know, if one day COVID decides to leave our planet and you're in, I don't know, Disneyland or something, you can make a trip to Santa Barbara, like, to let me know. I would show you around the lab, the place. And if you're interested in other opportunities also, I'm happy to hear and work with you. Okay, that's a moment to stop.
Okay, thank you very much, Pedram.
Sure, sure.
I think it was very nice. I'm sure there will be talks and virtual club from everybody. So I think we can take questions now.
Yeah.
People want to put them on the chat, or they can even unmute the mic and ask directly if you want to say your name and
I would have a question.
Yeah, Mark is there.
Mark, how's it going?
Okay.
Hi, Pedram.
Hey.
Okay, I have many questions. I'm gonna make it short. Only choose one or two. Maybe we can talk about the MBL. It's maybe something that you are more involved in, or so yeah. There's this concept of monogamy of entanglement. I'm not super aware of. So the way I understand it, you tell me if it's right. It's like if I look at the entanglement between two qubits, it will go down once it starts to entangle with the others. Is that what you showed?
Yes, exactly. Exactly.
So is it the way that you used to look at this Jij, or how did you measure this Jij till
Yeah, that's a good question. Okay, so back to this. Okay, this is how we measured it. There are two. You put a qubit in an equator to be sensitive to phase accumulate, and it starts accumulating phase. This accumulation of phase related to its surrounding dynamics, okay, and could have a couple of components. So it has a fast component, slow components. But then in the nearby qubits, to show that that nearby qubit is important in this dynamic, you originally have it on the blue state, the nearby qubit, the J qubit, 0 state, and you record the sigma x on qubit I. And then you flip the state of, and that's, you get the blue curve. And then you flip the state of the J qubit. In the case of Anderson, it shouldn't make any difference because they don't care about each other. In the case of many-body localized, you see the dynamics get shifted. The fast component or whatnot could be affected too much, or very different. It would not change. But you see the slow component is shifts a little. So this is what this is. Okay, 1, 2 oscillation this is 2 megahertz, and then we went to 1, 2, 3, 4. So we went from 2 to 4 megahertz. So there's 2 megahertz of coupling between these two qubits. And then I Fourier transform blue and red, and we subtract the position, the dynamics.
But when you do that, do you assume that all the other qubits do not play a role, or they would be in very like higher frequencies, or like?
Well, we are making a differential measurement. So they are doing whatever they are doing that is giving this 2 megahertz. But when we make one change and then we say it's dominated by this change, what we're going to measure. So it's a differential measurement. All the other qubits are putting together, leading to this, whatever is blue is doing. But now you just make one change and claim that is dominated by the change in the blue qubit.
I see. Okay.
A quick question on this. So you always have up to, you flip 1 or maximally 2 photons, like in our old stuff, or you put more?
I think no. We got lazy. I think we should have more. We could have more photons in the system. It matters that you make only one change. You know, you can have one flip. You can have photons on other sites. I don't remember. We might have photon on other sites when we did this experiment. Maybe we had photons on site 8, 9, 10 or somewhere, which we don't make a difference.
And this is up to 15?
This is done in a chain of 15 qubits.
Right, and then you can do I minus j up to 6. Okay, so.
Yes, right, because it dropped too small.
Right, right. Is it okay? So there's no boundary issues also. I mean, the 15, you go up to 6 is okay, I guess.
Well, it's proof of principle or something. It was a bit taking too much time. Otherwise, we could have gone 2D or whatever. The goal was to map out the full wave function of how it extends beyond other qubits, and it kind of, in a sense, it is this plot saying that, look, as if it's about 3 megahertz and then going down and down. Essentially, you can think about it as a spatial pattern. Sorry, I'm missing the axis here. This is I minus j. Well, maybe you can. This is a cut to the wave function, essentially, tau wave function.
Right, and this is all static as
overlap.
well, right? No modulation here. You treat the Hamiltonian.
Yes, yeah.
No modulation. Okay. All right. So there are more things to chat, but we can do it afterwards. Let's see if anybody else from the audience wants to ask a question. I see Victor raise his hand, and is anybody else? Please raise your hand or put it in the chat. Or so. Okay, Victor, go ahead.
Hey, Pedram, very nice talk as always. I enjoy a lot. Very beautiful. Awesome. Pedram, I'm very interested in the OTOX part. So I wonder if you can, when you do the OTOX, the unitary you apply is a random unitary, or you can also have many body localization in this kind of system.
We can do many body localized. I think you have to tell me the key difference between this experiment and quantum supremacy experiment was that after butterfly, everything has to be mirror symmetry, meaning every gate in here has to be inverse of that gate. So if you give me a U, which we can implement its inverse by inverting the gates, then we can do it. Yeah, I think you can study many body localized phase. Yeah, you can slow the dynamics and whatnot and see what happens.
Right. Maybe if you are in the MBL phase, if the butterfly is far apart, maybe you can almost come back to the initial state. Right? Maybe the butterfly don't.
Because Texas is in lockdown and is not accessible, right?
Yes, maybe.
Yes, right. You know, yeah. I mean, yeah, exactly.
Yeah, it's interesting. We can do a bit on that. I see more questions. Victor, feel free to join the chat after the talk. I'll send you the link. It's not easier for the chat.
Thank you.
There is
Latore, our director, is raising hands. Please, Jose.
Hi, yeah, I had questions about the benchmarking. Okay, so actually two. One of classical benchmarking, whether you ever consider to use tensor networks to mimic the classical computation, because tensor networks have proven very powerful in other contexts.
Yeah, it's beyond my knowledge, but I think yes.
Yes,
yeah.
You tried, or yes, you did it, or?
Well, let me see. Yeah. I mean, the computation was definitely scrutinized very heavily, and I'm sure they used it.
Because there is no
I
mention.
can show you, huh? I didn't say how it was.
No, I read about all the Schrödinger-Feynman technology, but tensor networks is really completely different.
Okay, here is a summary of, but this is just a bunch of abbreviations which I don't understand much.
So PEPS is two-dimensional. This is PEPS, like PEPS, the two-dimensional tensor networks, or I see, or something.
I wouldn't be able to say something intelligent about this, but
okay. And the second question is, have you done benchmarks on very common things like the quantum Fourier transform? I mean, can you?
No. We use
just see the fidelity when you do something like that. That you know perfectly okay the final result, but yeah, you have to do it on the quantum.
Well,
you mean a non-quantum algorithm, like something with specific value?
Yeah, but those algorithms, if you
it's very deep circuits, right?
Very deep circuits. If you do it genuinely, and you're not gonna, at the end of the day, you got to truncate and stop it somewhere and compare it with a classical computer. So random circuit is as good as it needs to be. What we do commonly is we do OTOC without the butterfly. It's called Loschmidt echo, which you apply sequence of gates and to fully invert it to come back to identity, and you see how often it doesn't come back to identity. So you don't need even any classical computer or anything. You just apply U and then U dagger and see how well they cancel each other, and then it gives you a notion. But the key, the big thing is that the product of individual fidelities is sufficient to tell you what's happening. I think this black line is very, very important finding.
Actually, it's a good question what Jose mentioned. But to my knowledge, I don't know any of the. I think most of the ones that produces a specific number or something you can benchmark, like frequency, as you said, in Fourier transform, require hard things like phase estimation, algorithm, something that is very difficult to implement so far. Maybe it's a good direction to think what's. I'm sure the computer science colleagues have thought about it, but something that is Nisky.
When you're, it is also, you got to be sure it doesn't get affected by readout or state preparation, right? A spam error. So local observables in the ergodic phase is usually tend to go to 0, tend to go to the dimension of, they get thermalized quickly. The subsystems get thermalized. So these numbers are usually in the order of 1 over dimension of the Hilbert space. So they're really hard to read. And then if you could manage something large, then to measure also, you have lots of, you would be dominated by readout error or state preparation error. And it's just, it's hard to come up with a number, say, hey, look, this number meant to be 0.5. Did you measure it or not? Is not easy. But also here you can see that, you know, fidelity of the gates is sufficient to predict the fidelity of the circuit, of the operation.
Right. Any more questions? Anybody? Can see. Anybody else? I see the race has are still from before, right? I assume the 2 ones. Victor, have you raised your hand again, or is it before? I'm a bit confused.
I love it, Dimitris.
Ah, you lower it. Okay. Okay. Still understanding the Zoom. Anybody else? Any other questions, comments? Maybe you can briefly show that last slide you skipped about the future, the last before last.
Yeah. Let's talk about future. So I mentioned something about NISC and what we can do with error without error correction and only with error mitigation. So here is a summary of our speculations on this matter. Okay, right. So it kind of says that what is next? If you ask me what is next, I would say our current understanding is that fault tolerant takes lots of qubits, but they don't need to have very high fidelity. They can be 10 to the minus 3 gate error. But if we hope to solve problems without error correction and just relying on error mitigation mainly, you need to have much better qubits, or you can have the same quality qubits, but error mitigation can effectively bring you to these very low errors. So there are 2 ways forward if you're hoping that NISC algorithms could result in anything. One is we make qubits and gate operations far better, or theorists do their job and make error mitigation ideas that allows to have effective gate fidelities that are 10 to the minus 5 and 10 to the minus 6. And as you can see, the first group of problems that come to horizon seems to be non-equilibrium dynamics related to condensed matter problems, let's say. They are not that far from rich. And then fermionic problems where you have to kind of need twice more qubits, and you have to deal with Jordan-Wigner transformation, and the geometry of the system become irrelevant in a sense that everything maps to 1D geometry, and you need to have long chains of qubits. and you have to figure out how to study fermions with systems that are excitations are bosonic. So these kind of problems start coming to horizon. So you don't need to have that many qubits for near-term applications, but you need to have really good qubits. So you can choose to go upward in this plot, or you can choose to go to the right. Either way, doesn't sound easy.
Right. Okay. Anything else? Anybody has any last question or comment?
Oh, there is this.
If not, thanks everyone again for joining in today. Thanks for a really nice overview of many different things, Pedram, from
Sure.
last year to most recent stuff. Great to see condensed matter is coming into the game again. We can chat a little bit more now in the other chat.
Sure.